Hi everyone. So finally, we're going to be talking about applying and interpreting logistic regression in Python. And let's note both of the approaches, the data science approach and the more regular science approach. So in the data science approach, which is more focused on model building, we may want to create two sets from the original data. So here we're going to import the scikit-learn train test split and logistic regression model. And we're going to do the train test split on the data. So remember that we usually have a X data frame of a multi-dimensional matrix. So that is an X of multiple columns and a Y of only one column. So the Y is the single outcome variable dimension. And the X here says just X1 is multiple. We may use multiple predictor variables, one or multiple. And let's highlight here. And from this train test split, we create a train set and a test set. And typically the train will have 75% of the data, and this is the original data here. And then test set will have 25%. Then we build the model and we fit the model. Notice we're fitting the model with the trained data. Create the model is here, and then we can use the model to assess the accuracy of the model. And we can assess the accuracy within the trained data itself, and then we can assess the accuracy with the test data. And this logreg.score, this is the score function of the logistic regression model, and it's the accuracy. It's the accuracy measurement, which you can take a look back of how accuracy is exactly measured from our confusion matrix lecture. Now, the other way to do it is the more regular science approach, and I also have the code here for that, and we can use function from the statsmodels.api package. So we import that package, and then we use the logit model, and notice here that first of all, this is inverted. Y goes first, and then X. The same case, though, the Y is one dimension. It's the outcome variable. And then the X may be multiple variables. And here we create a logit model. And after that, we need to fit the model. And then the model's in the results here. And then we can use the summary function to print the results. And you're going to see something like this if you use this package. There are actually other packages you can use, but this is a good one. And if you remember this from linear regression, this looks like the kind of standard result from linear regression. So in this model here, I used diabetes data. So diabetes 1 or 0 was the binary outcome variable, and the X was multiple other variables like glucose and blood measure and BMI and whether the person was obese or not, which is a binary variable, and I calculated that if the BMI was equal 30 or above, it was obese, otherwise it was not. So this is the only binary variable, and the other are actually all numeric variables. So we have a number of information here, a number of observations on the data, so it's 1000. The pseudo R-squared, so the R-squared is another measure for logistic regression. It is not one of those that we discussed in confusion matrix used for classification like accuracy. You can use those, of course, but also we can use the R-squared, which we interpret the pseudo R-squared for logistic regression, which we can interpret just the way we interpret the R-squared for linear regression, OLS linear regression, which is the amount of variation in the outcome variable explained by the whole model. So write that down on how to interpret R squared. And here it's really bad. So that's actually 0.02%. That's how I interpret. So 0.2%. So the pseudo R squared is 0.2% of the variation in the outcome variable is explained by this model. So this model is really terrible. And I'm sure it's because the data is not real data. I think this data was one of these data sets that is available on the internet, and it's not actually real data. It looks like real data. It fits into the model for our exercise, but it's not representative of the world. There's some other measures here, these log likelihood measures and the log likelihood ratio p-value. We don't need to worry about them, but also they indicate that the model is not good. Usually p-value, you will remember, you will want low p-values to suggest that we are seeing something important in the model. And here we have very high p-values. When we go to the coefficient of this line, this is the, if you remember back from linear regression, we interpreted this similar, not the same, but similar way. This is the impact that each of the predictor variables have on average on the outcome variable, controlled for all the other predictor variables, which is one of the beautiful things about regressions, that they are capturing the association between each predictor variable and the outcome variable, considering all of the other variables, controlling for them. But unfortunately, if we look at the p-values over here, this p-values listed here, they are all very high, which means that these associations are not significant, except for this one here. So this is less than 0.05. However, it's a negative relationship. Okay, so that means that when BMI goes up, diabetes goes down, which does not make sense given what we know about medical theory. Therefore, there is something really wrong with this data. Now, you can also try different model with different predictor variables, but I think there's really something wrong with this data. So it's you just need better data. Now, let me point out some things here. Okay, model results are not great based on these pseudo R squared and the log likelihood measures. Now, let's take a look on how to interpret this. So remember, the results are in log odds. So what happens is, let's interpret BMI, which is a continuous variable. So what this model says is that for every unit increase in BMI, there is a the log odds of having diabetes decreases by 0.0361. Now, it's difficult to interpret what this is. So what can we do? Well, okay, example on how to interpret. I think this is the same thing of what I just said here. So what can we do? Well, we can translate the log odds to odds, because odds, at least an odds ratio, it's more interpretable. And I'm giving you here some code on how to do that. You can use the NumPy exponential function. And if you want to just do number by number, you can just apply this function here into the specific value that you want, like the coefficient. So you could just do something like np.exp. I'm sorry, this is really terrible. And you put the number 0.0361, negative 0.361, and you find the actual odds ratio. But here, the way I'm doing, I'm applying it to the whole data frame. And you can copy this code, and then you get a better table like this, and you still get the odds ratio, and then you get this the standard error window and the confidence interval. And here this is much better to interpret. So these are in odds ratio. So I have some table here for you to serve as guidance. If it's equal to 1, it's the same odds. If it's less than 1, then there's fewer, and if it's greater than 1, means it's greater, an increase in odds. So let's take a look at BMI again. How to interpret this? Now the number is 0.96. So for every unit increase in BMI, on average, the odds of having diabetes is multiplied by 0.096. And because this is less than 1, this is a decrease. That is, it increases by a factor of 0.96, which is effectively a decrease. Another way to say is that every unit increase in BMI reduces the odds of having diabetes by 4%. You can actually translate the odds into percent by subtracting it from 1. So if it's less than 1, you subtract it from 1, and if it's higher than 1, you subtract 1 from it. Let's take a look at another example. So let's take a look at obese. Now this is a binary variable, but it essentially works the same way. So if the person is obese, on average, compared to those who are not, the odds of having diabetes is 1.32 times greater. And I'm getting this from here, 1.32. That is to say, if a person is obese, on average, the odds of having diabetes is 1.32 minus 1, which is 32% higher compared to those who are not obese. So that's how we interpret the results of the logistic regression. Now, this model is really bad, so these numbers are just for exercise purposes only. This is not a real or good data from what I can gather. So I hope this is useful to you, and I will see you next time.